Right, so let's go ahead and get started. Hi, everyone. My name is Julia Matevosyan. I'm an Associate Director and Chief Engineer at Energy Systems Integration Group, or ESIG. And I would like to welcome you all to ESIG's webinar. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of clean energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. For those of you who are members, thank you so much for your support. It makes it possible for us to do these webinars and other work with you. Using this opportunity, I would also like to invite you all to upcoming ESIG Spring Technical Workshop in Austin, Texas, so in my backyard. And that's the week of March 17th. As always, the workshop will host a mix of technical content with additional focus on large load integration. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime at ESIG website at www.esig.energy or find us on LinkedIn, YouTube, Facebook, and X. Okay, just a few logistical matters before we get started. First of all, participant lines will be muted for the duration of the webinar to avoid unnecessary distractions. For Q&A, please go to Slido platform at slido.com, enter ESIG 18 as event code. The instructions are also at the bottom of the screen right now. You'll see a thumbs up button next to questions, and this allows you to cast your vote and ask to prioritize questions that are submitted. We plan to save 10 to 15 minutes for Q&A at the end, and then wrap it up at the top of the hour. An email with the link will be provided once the video has been posted. We also plan to provide short responses to all unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. So to introduce today's topic and speakers, the widespread integration of inverter-based resources, or IBRs, has led to increasing instances of oscillations in power systems driven by factors such as control interactions amongst inverter-based resources in low system strength conditions. In particular, sub-synchronous oscillations have been observed in regions of Australian grid with high concentration of inverter-based resources. When such oscillations are spread across a large portion of the network, it becomes crucial to identify the root causes and to enable both operational mitigation and exploration of long-term solutions. So this webinar today will review recent IBR-driven oscillations events in Australian grid and proactive steps that were taken by Australian energy market operator AEMO to investigate these occurrences. The webinar will provide actionable insights into using advanced approaches such as impedance-based assessment to address challenges posed by widespread adoption of inverter-based resources. These methods are offering both immediate and strategic solutions to enhance grid stability. The webinar will be presented by Nilesh Modi, the Manager of Future System Studies team at AEMO, and Shahil Shah, Principal Engineer at the Power Systems Engineering Center of National Renewable Energy Laboratory, or NREL. Nilesh has 17 years of experience spanning across academia, research, and industry. His current area of interest is power systems operation with high share of inverter-based resources. Nilesh received his PhD from University of Queensland, and he is also recipient of ESIG Excellence Award. Shahil's research focuses on stability of power systems with high levels of inverter-based resources, with specific emphasis on impedance-based frequency scan methods for stability analysis. Shahil led the development of Grid Impedance Scan Tool, or GIST, at NREL, an advanced platform for performing impedance-based stability analysis. Shahil received his PhD from Rensselaer Polytechnic Institute, and he is also a recipient of ESIG Excellence Award for his leadership in design and analysis of grid-forming inverter systems. So just a short reminder once again, please use Slido at slido.com for your questions. The event code is ESIG 18. And without any further ado, let's go ahead and get started. Shahil, Nilesh, I turn it over to you.
Thanks, Julia. Hope you can hear me okay.
Right. Loud and clear.
Okay, thanks. Hello, everyone. Nilesh Modi from Australia, along with Shahil Shah. So today we are discussing the analysis of the IBR-driven oscillations in the Australian grid. So this would be the content for next 40 odd minutes. So I'll start with a bit of a background. I'll give you more information about the West Murray zone oscillation, 17 Hertz oscillation, which AEMO has been seeing for some time. Some of the interesting observation from real-time data analysis, the issues and the challenges of identifying the root cause of this oscillation, and once we found the cause, how it was replicated in the power system simulation tool, and the remediation measure which were put in place working with various participants in West Murray zone area. Then I'll hand it over to Shahil, who will go through the impedance scan and how this tool can be used to identify the root cause of oscillation. At the same time, how this tool can be used to size the grid forming resources to achieve a specific grid strength and to eliminate these oscillations. Now, before I go any further, I would like to acknowledge and give a great thanks to various organizations who has supported this investigation. City Power, Power Core, who are distribution businesses, business in that part of the network. CT Lab, who provided a high resolution meter, which help us to further understand the oscillation in that part of the network. Osnet Services, who are the asset owners, asset owners in Victoria, and NREL Laboratory. I would also like to thank various teams within AEMO who has helped through this investigation, and most importantly, market participants and OEM who has supported with the information to investigate these oscillations. So a bit of a background on the West Murray zone. On the right side, you will see a national electricity market of Australia, Eastern Coast power system. And the one highlighted is the West Murray zone. If I can bring up the pointer here. Okay. So this network West Murray zone is consisting the areas of Southwest New South Wales, which is here, and Northwest of Victoria. It has a large number of inverter-based resources connected, wind farm, solar farm, batteries. There are SVCs in there and HVDC links, so it's kind of a perfect storm for inverter-based resources interaction. It is largely a radial network, a 220 kV network, and in the weak part of the network. More recently, there has been some installation of synchronous condenser in that part of the network, which has improved the system strength or grid strength in that part of the network. Give a bit of background on 17 Hertz oscillation. It was first identified as a byproduct of investigating a system incident. Since then, AEMO has been closely monitoring that part of the network through the high resolution PMU measurements. What we have observed is the magnitude of this oscillation has been varying. At one of the node, we have seen the maximum 2.2% oscillation peak to peak, but most of the time the oscillations were in the range of 0.5% peak to peak. The interesting bit about these oscillations were that the duration of the oscillations were ranging from few seconds to several minutes. So often it comes on and goes off. And it was appearing without any major disturbance or system configuration change. So it was very difficult to identify the cause because there wasn't any clear correlation with the system disturbance. When we started looking at the characteristic of oscillation, there was some consistent observation which we could see. The first one was these oscillations were contained within northwest of Bendigo and west of Darlington Point, which is basically saying it was contained in a West Murray area. As we move away from that area, the presence of this oscillation were not noticeable in the high resolution measurement. These are the two snapshots of two events. There were a number of events we have observed, but this is just example to show how it looked like in a high resolution measurement. The most interesting bit of this oscillation was a gradual increase in the oscillation. So like I mentioned that there was no clear disturbance which led to this onset of oscillation, and you can see there are 3 figures on the top where you can see it's slowly started to appearing, and then it slowly disappears as well. So that was a bit of a mystery for AEMO engineers and the market participants as well. We started requesting the data as soon as we found out the oscillations are appearing on the grid. And obviously, we'll start with any relationship between QV or PV. We requested the data, and then looking at the high resolution measurements, we couldn't establish there is a clear correlation between QV or PV for any of the IBRs in that part of the network. So that was one of the things which was found interesting, because normally people would say, okay, look at the QV and look at the PV, and you should be able to find out the which IBR is causing that that oscillation. Some of the other complexities were, at the time, we had a very limited high resolution visibility. There were only a couple of PMUs available to AEMO. So we had to go and request data from generators, and then once the data comes in, look at the data and try and analyze the event, which takes considerable amount of time. As I mentioned frequently, it was intermittent oscillation, so it was variable in duration and magnitude as well. After looking at this relationship between Q and V and P and V, we started looking at other factors that can we find any clear correlation between any quantities. We started looking at the line loading. That wasn't any clear correlation. These are some of the feedbacks we received from the industry that prompted us to look at this correlation. Was there any clear correlation with the active power generation or reactive power generation from the IBRs? Is it only happening during low IBR generation or high IBR generation? We couldn't establish any clear correlationship. There was some discussion about impact of the load in that part of the network. Maybe the load is picking up and then it is exerting this oscillation, but there wasn't any clear correlation we could find. There was the HVDC link, so some of the literature suggested that HVDC link could have an impact on this or could be a cause of the oscillation. But when this HVDC link was out of service, we could still see oscillation. So that's the status of nearby HVDC link was also ruled out. We looked at the status of the SVCs and the mode of operation of SVC. We put one of the SVC in a manual mode, Q control mode, just to isolate that is it a cause or not. But we couldn't find any correlation with the SVC as well. So this lists out the complexity we have. Like it was like a mystery to us until one of the engineers thought, okay, maybe we should start looking at the irradiance. And surprise, what we found is there is a clear correlation between the irradiance change and the onset of oscillation. We started looking at one event, and there was a correlation to it. One of the IBR was when the irradiance at that particular IBR was dropping, it was coinciding with the onset of the oscillation. We started looking at number of events, and it was consistent. We looked at almost 8 to 10 events, and almost every time when irradiance at one of those IBR was reducing, then the onset of oscillation was starting. So that kind of gives us an idea that, okay, that there is a clear correlation between irradiance change and the onset of oscillation. But like me, many of people on the call would be a power system engineers, and they wanted to model it, right? Okay, well, that's just real-time incident. Can we model it through the power system tool? So we started looking at the modeling of this event to identify or at least relate this real-time observation with the modeling. We divided the power system modeling in 2 parts. We started looking at the SMIB analysis as well as the wide area analysis. So in the SMIB analysis, as it says, the single machine infinite bus kind of a setup, we started looking at individual solar farm, which we thought could be the cause of this oscillation in isolation. we used the site-specific vendor model, which was provided to us through the connection process. Started looking at SCR and X-wire ratio of a typical snapshot. So try and expose those IBRs to typical SCR and X-wire ratio, which they would likely to see during real time. Applied a gradual reduction in irradiance without changing the active power set point. So it's keeping just slow change in the irradiance. And we also did some sensitivity on variation in SCR of each of the solar farm. And we could easily see that there is a relationship between the irradiance change and the onset of oscillation. Then we started looking at the wide area simulation. So we looked at the 4-state EMT model, which we have. We set up the case to certain conditions and started playing with the irradiance change at number of IBRs and then see which one is actually causing it. When we changed the irradiance at one of the solar farm, so we started looking at one solar farm each, as I mentioned, but there was a consistent observation that when we changed this slow irradiance into one of the IBR, then it was showing the oscillation on the grid, and it was propagating all the way in the West Murray area. So this is a setup of the SMIP analysis. So we picked up most likely 4 that we thought could be worth investigating, the IBRs. We looked at various operating point, although on the slides only 2 of the operating point is mentioned, 1 per unit and half per unit. And we slowly started reducing the irradiance at those IBRs, and then we could see that was undamped oscillation in IBR number 1 at 1 per unit active power set point, at the same time half per unit active power set point. There was some interesting other observation we also noticed in the modeling exercise, that there were another IBR which was showing a very brief excursion of 22 Hz oscillation, but they were damping down within a second or so. And similarly, there was one IBR which has a 25 Hz mode sitting in, but it is well damped. And later on, Shahil will probably show you that there is a well damped 22 to 23 Hz mode in that part of the network as well. So going a little bit further on looking at the wide area modeling. So the one on the left hand side is you can see the response of the only one bus. I have shown it here, a response at or the voltage measurement at one bus. In the simulation, you can see how gradually it is growing. And on the right hand side, you can see the field measurement and the fingerprints are aligning, right? So you can see that, okay. Similar observation, which we noticed through real time measurement, can be replicated in the EMT model, right? So particularly when we change the irradiance at only one IBR. Going a little bit further, so on the left hand side you can see the West Murray area voltages, so voltages at those buses, and you can see this is the one where you see the presence of oscillation. They are within the West Murray area, and the bus where you can see a very small tiny oscillation, they are towards the boundary of the West Murray area, and you can see this is aligning with what we observe in real time. So kind of simulation is matching with the real time to a certain extent. When we change the irradiance at other IBRs, then you can see there isn't any clear oscillation observation in the simulation modeling, which is again telling us that there is one IBR which could be causing this oscillation. Then we started working with various market participants and OEM. Had a bit of a discussion with OEM and market participants. They looked at their flight recorder data, and then they could see that, okay, well, there is some kind of a thing going on in the DC link control. Working with OEM, we managed to sort out this oscillation, or at least had a good handle on this oscillation. So what they did is they provided us the improved DC link control strategy. So they improved their control system on the plant. We tested that through the modeling. So similar exercise what we did in SMIP and the wide area modeling. We repeated that with the new control tuning. and we could see that it is working well as expected. Then we went on the field and then implemented those settings on those inverters, and then wait for the irradiance change and then see, can we see a clear onset of any oscillation in that part of the network. And the one on the left side, you can see this is a field measurement before the control system upgrade was put in place. There were a number of instances where we could see this kind of oscillation. And once the control system was in place, you could see there isn't any presence of those oscillation in that part of the network. So that's a brief of investigating 17 hertz oscillation in the West Murray area and how we managed to replicate that through EMT modeling, and working with market participants and OEM managed to get improved control system on the ground, and it has helped to reduce the oscillation in that part of the network. With that bit of a background, I'll hand it over to Shahil, who would go through how the impedance scan tool can be used to improve the understanding of the root cause of oscillation. Shahil, over to you.
Yeah, thank you, Nilesh, for that overview. Can you hear me okay? Yeah, great.
Yes, yes, perfect.
So I'm going to cover two topics. One is the impedance scan analysis to identify the source of oscillations that Nilesh described. So really how we can understand the source of these oscillations in an organized manner and get more insights. And the second part would focus on how to size grid forming resources near some of the weak grid regions to avoid these oscillations. So in the first part, let me give a high-level overview of what is impedance-based stability analysis method. So as you can see on the top, we can represent IBR as by its impedance, ZI, and then grid by its impedance, ZZ. And in the impedance-based stability analysis, we just need impedance response of the IBR and the grid to understand if they are interoperable or they are stable together or not. Uh, these impedance responses can be obtained from EMT models, from field measurements, or directly from the experimental measurements. The one key advantage of this approach is that we can use black box models. We don't really need any analytical models to obtain the impedance response. The second key advantage is, as you can see here, like I've represented the IBR impedance and grid impedance as puzzle pieces. So what you can do is, for example, for the IBR impedance, you can have 4 or 5 different impedance responses for different operating conditions. So that represents 4 or 5 puzzle pieces representing IBR. You can have this same impedance set of impedance responses that you have scanned before for the grid. And it can be from different points of interconnections. It can be for different dispatch conditions. And once this impedance responses are obtained, they can be stored in some repository, and you can mix and match any IBR impedance, any puzzle piece that represents IBR, and match it with the grid and see if they will create an instability or not. When you connect the two impedances, they form a negative feedback loop. So to do this stability analysis using this impedance responses, we plot either the Nyquist plot of impedance ratio of grid impedance to IBR impedance, or we just compare the impedance responses. There are two different forms of impedance-based stability analysis, standard criterion, in which we assume that IBR and grid are separately stable, or these puzzle pieces are separately stable. What happens when you connect them to each other? What happens to the stability? The second criterion is reverse criterion, where we assume that the IBR and grid, when they're connected, that they are stable together. Now, what happens to the stability of the grid if we disconnect the IBR? So we are really trying to understand if removing the IBR is causing any instability, or that IBR is basically a stabilizing device. I won't go into more details, but these two criteria together are very complementary. They enable the impedance-based stability analysis to apply to large systems in a feasible manner where it can work on real systems. So there are three main steps to do impedance-based stability analysis. And the first step, we identify IBRs, which we think are the likely source of oscillations, as Nilesh described, from field measurements, particularly if you're looking at post-event diagnosis. Or for the planning, we just keep the step 1, but for planning studies, we'll just look step 2 and 3. Step 2 is we perform impedance scans of IBRs in single machine infinite bus format. And what we really do is we are trying to obtain those IBR puzzle pieces for different operating conditions. The goal here is to understand if those IBRs have any resonance modes. And the second goal is if there is any SCR, short circuit ratio based stability boundary, like for example, certain PV plant or wind plant is not able to operate stably below a certain grid strength, below a SCR of, let's say, 3. Uh, once we do that, we go to the step 3, which is where we obtain impedance response of wide area grid using the wide area EMT model. And then the grid impedance response is obtained from a POI of particular IBR for different dispatch conditions within the grid. And those are basically giving you the puzzle pieces that represent the grid. And now you can mix and match and understand how this particular IBR that we have selected is impacting the stability of the grid, impacting the damping of certain oscillation modes. And then we repeat the steps at other IBRs. Uh, if so, let's see what we require to do these 3 steps. For step 1, which is basically for post-event diagnostic, you really need field measurements. For step 2, you need only IBR models. You don't really need system models. And for step 3, you require both IBR models and system models. So as a system operator or owner, uh, there are certain insights that you can achieve just by doing step 1 and 2. Step 3 is something which will give you concrete or exact answers, but then you need to have a system EMT model. So let me demonstrate this step 2 and 3. Nilesh already talked about step 1. So I'll talk about step 2 and 3 very quickly. So stability analysis of a PV plant in a single machine infinite bus format. So on the left, I'm showing the impedance response of a particular PV plant. And then we did that impedance scan for different operating conditions. For low irradiance conditions, just like what Nilesh observed in the field measurements, we also see that for low irradiance, there is a resonance mode in the, let me try to see if I can find a pointer. So that is this, oops, this is not what I was looking for. Anyways, I think I can do with this. So we find an underdamped mode for low irradiance condition. Now, once you have this impedance scan, which shows that there is an underdamped mode, within a second, you can determine if it is stable for a particular short circuit ratio or not. And then we do that, plot the Nyquist plot of impedance ratio for different SCR condition or for different grid strength condition. And we find out that for SCR of less than 3, the Nyquist plot encircles the critical point, basically this -1 point, and that shows instability. So what this tells us is that this PV plant will become unstable under low irradiance condition if the grid SCR is less than 3. Now that is good. We got some insight that some of these plants are probably the source of oscillations. But the actual grid SCR based on positive sequence analysis was significantly higher. So that still doesn't completely explain the source of oscillations. So we go to step 3, where we take this IBR impedance response, or basically the puzzle piece, which represents the worst impedance response of the IBR in terms of stability, and try to match it with different grid impedance responses, and which is on the right. So here I'm showing the impedance response of the West Murray Zone grid obtained from wide area system EMT model for 4 different conditions. And this is from looking from the POI of this particular PV plant. So the pink one is when there are 2 other PV plants in proximity which have low irradiance. And under that condition, we see that there is a big there is an underdamped resonance mode at 73 Hertz. If we have only one PV plant with low irradiance and proximity, the impedance response of the grid changes to blue, which has a resonance mode at 73 Hertz, but it is more damped. And for when these PV plants in proximity have high irradiance, or when they are not connected, we see this black or red traces, which doesn't have this resonance mode. So when you use just the short circuit ratio, you are assuming that the grid impedance is inductive. It is just flat like a line. But these other IBRs in the grid, which are in the region, they're creating this high impedance or resonance mode at 73 Hertz, which in the rotating reference frame becomes 23 Hertz. So now let's see how our IBR impedance matches with this grid impedance. And then we plot this Nyquist plots here. So when we use the red grid impedance, which is when the other PV plants in the region have high irradiance, and compare it with or match it with our PV plant that we are analyzing, which has low irradiance, uh, the Nyquist plot doesn't encircle the critical point. It basically shows that the IBR plus grid are stable. And again, this we do this without running any additional EMT simulations. You just need impedance responses. When we use this blue case of the grid, that is the stability reduces because the Nyquist plot gets closer to the critical point. And then when we use the pink trace, it encircles the critical point and showing that the grid and then the plant becomes unstable. So that really shows how grid and IBR together, like how we can do mix and match to understand stability. To look at it in a different perspective, we can also look at what we call modal impedance response. So here the circles, they represent the modal impedance of the grid without this PV plant where we are doing this analysis, where we are connecting these two puzzle pieces. And when we connect the IBR impedance to the grid, or basically IBR to the grid, the modal impedance becomes this response that I'm showing through stars. And what it shows is that a grid resonance mode at 23 Hertz moves to 17 Hertz and it becomes unstable. So this particular PV plant is moving a 23 Hertz mode to 17 Hertz and it reduces its damping to a negative value. So it really shows you how the PV plant is impacting the damping of already existing mode within the grid. Now we repeat this analysis at different IBRs, and as Nilesh was saying, like 4 or 3 IBRs were found to be the key source for this oscillation. So I'm just showing you the summary of analysis of 3 PV plants. On the left column is basically PV plants with low irradiance. Here is the resonance frequency and damping within the system for that particular condition, and then the oscillation risk. Let me start with the bottom row. So plant C, if there is only one plant in that region, plant C with low irradiance, there is no resonance mode in the system based on the impedance analysis, and the oscillation risk is none. When there's a plant A only with low irradiance, there is a 23 Hertz mode, but with very high damping. And plant A and C are within the system, there is a 23 Hertz mode with slightly lower damping, but it is still sufficiently positive. So there won't be any oscillations. And then if only plant B is in the system, which is basically the plant for which I showed you the analysis in previous couple of slides, the system mode is at 17 Hertz and the damping is positive. So the risk of oscillations are still low. But when we connect either another plant, plant A or plant A and C together with B, then as I showed that the resonance mode moves to 17 Hertz from 23 Hertz, which is created by plant A and C, and the damping is quite negative, and we have high risk of oscillation. So in summary, plant B is kind of necessary uh, ingredient, particularly when it operates at low irradiance condition, to have these oscillations. And then plant A and C makes it worse. So now you can kind of rank the IBRs which are contributing to this oscillations and try to dedicate where you will do the control upgrades, which plant you will prioritize to either make changes to the system or make changes to the controls to mitigate these oscillations. So what I talked about was all about detailed analysis of understanding where the oscillations are coming from, but how do we mitigate them in the planning stages, and how do we size grid forming resources to provide specific grid strength? So that is what I'll talk about in next few slides before moving on to Q&A. So here is a plant, 200 megawatt plant, not those 3 PV plants. This is a different plant. Again, we are using black box models from AEMO, and this 200 megawatt IBR plant becomes unstable whenever the grid short circuit ratio becomes less than 3. And that we can also confirm from this time domain simulation of plant in single machine infinite bus format, where we reduce the SCR from 4 to 2.5. And then eventually plant starts oscillating at around 6 Hertz and then trips. So really showing that this plant cannot operate when SCR of the grid at POI is less than 3. Now, to size the grid forming resource, we need to have a defined objective. So the objective that we have is we want to stabilize this 200 megawatt IBR plant using a grid forming battery storage at the POI so that it can operate stably when SCR is 1.5. So how do we do that? So we have made several presentations and papers on how to quantify the voltage source behavior of grid forming resources using Q by V and P by theta scans. Basically, they are scans of transfer function from voltage magnitude to reactive power output of grid forming resource, as well as from the phase of voltage at the POI to the active power output. And this scans can show you the quantitatively what is the voltage source behavior, or what is the grid strength that the grid forming resource is providing. And this is like we are comparing the Q by V and P by theta scans of an ideal voltage source with a reactor. And both the scans for an ideal voltage source with a reactor are basically a low pass filter with negative gain. So they have flat gain at low frequencies. The phase is 180 degrees, so they're acting as a negative gain. There will be a resonance peak at the fundamental frequency, and then the gain drops over. We are primarily interested in transient to sub-transient time scales, so basically 4 to 40 hertz. And this is where we want to see this negative gain. Now, if the voltage is more stiffer, for example, if this inductance is small, and then that grid forming resource is providing more voltage stiffness, that means these P by theta and Q by V scans will have higher gain. It will basically go up the gain, and that gain you can use to quantify the grid strengthening behavior from grid forming resources. We can use Q by V, P by theta scan. We can also use impedance frequency scan for quantifying the grid strength. I won't go into the details about how to do this, but here are a few links on presentations where there are more case studies about how to do this. So with that background on Q by V scan, let me go back to our 200 megawatt plant, which was becoming unstable when the SCR was less than 3. So for SCR of 3, for 200 megawatt base power and 500 kV of base voltage, you can translate its Q by V response to 1470 watt per volt. And this is through a very simple equation that you can find in some of the publications whose link I have provided in the previous slide. What it shows is that if there is a grid with SCR of 3, if there is a 1 volt change at the terminal at the POI, that grid will automatically dispatch 1470 watt per volt very fast in transient to sub-transient timescale, basically the 4 to 40 hertz. Now, let's see how the SCR of 1.5 looks like. The response becomes half, 735 watt per volt. So for that 200 megawatt plant, if I want to make sure that it operates stably with this grid, there is a deficit of 735 watt per volt that we need to supply to make sure that 200 megawatt IBR will remain stable for SCR of 1.5. So we took one IBR model, grid forming BESS model, and performed its Q by V scan. And then we found out that BESS is providing 7,000 var per volt approximately at its POI. And then that is connected to 66 kV bus. Now, if it is providing 7,000 var per volt at 66 kV bus, because POI of our IBR for which we are trying to stabilize, the response from this grid forming bus would be 924 var per volt. So this is just direct translation, like how much 1 volt change in the 500 kV bus translates to change in voltage in the 66 kV bus. So 7,000 multiplied by 66 divided by 500 will give you this. And what it shows is that if I connect this grid forming bus at the 500 kV POI bus, it will give me a 924 var per volt of response. Now, from the previous slide, we found that there is a deficit of 735 var per volt or Q by V response to make the grid behave like it has a short circuit ratio of 3. So 924 is higher than 735. So that means this grid forming bus should be enough to meet our objective to stabilize this 200 megawatt IBR at SCR of 1.5. We can actually go beyond that. We can get more information from this. So 924 watt per volt. Let's see how much SCR or grid short circuit ratio it is providing. So again, if for SCR of 3, if I need to have the SCR of 3, if I need 1470 var per volt of response, again, this translation from SCR3 to this how much var per volt gain, it's very simple through a very simple equation for both Q by V and P by theta. So if SCR of 3 corresponds to 1470 var per volt, it's just a direct calculation that 924 var per volt is giving you the grid strengthening of SCR of 1.9. So what it means is that with this grid forming bus, our 200 megawatt IBR can operate stably with SCR of 3 minus 1.9. So 3 is something that it required. Now 1.9 is coming from grid forming bus. So it needs only 1.1 SCR. So it's even better than our objective of stabilizing this plant to 1.5. And again, this is all using black box model, no simplifying assumptions on the models of either grid forming bus or the 200 megawatt IBR. So to confirm this finding, we connected this bus and ran this time domain simulations. And here is the plant which is supplying on the right 200 megawatt of output. We start reducing SCR of the grid from 4 to 2 to 1.5. It remains stable at 1.5. We reduce it to 1.25. It still remains stable. And then only at when it hits 1.1, it becomes unstable. Now this is when we are using Q by V scans or P by theta scan to size grid forming resource. It's slightly approximated approach because we're ignoring coupling between the active and reactive power. Somehow for this IBR, the analysis turned out to be exact, that it is indeed becoming unstable only at SCR of 1.1. That is because for this IBR plant, the coupling between active power and reactive power axis was quite negligible. So that we have to build some level of conservatism in this type of sizing because if we are trying to do this without using basically the exact models. So now, okay, how do we use this approach for sizing of grid forming without models or EMT studies? And that is the main one of the objective over here. How we can do that is we start with IBR developers can guarantee stability for grid with SCR above a particular threshold. Usually, most of the modern IBRs, they remain stable when the short circuit ratio or the grid strength is more than SCR of 3. Some are even providing at a lower level up to SCR of 2. But so developers can provide that their IBRs will remain stable, including as long as the SCR is above a particular threshold. Now, that should include all the balance of system, transformers and cables between the inverters and wind turbines and the point of interconnection. Now, system planner estimates, okay, if I'm getting this much amount of IBRs within this region, and if they demand particular grid strength, let's say a SCR of 3, what is the actual grid strength we have in the system? And that determines what is the available grid strength. And based on the difference between this demand for our grid strength and available grid strength, we find out the SCR deficit. And that SCR deficit can be translated to how much Q by V, or basically var per volt, as well as watts per degree, or P by theta response, we need for this IBRs to uh, see the grid as if it is above that threshold requirement. And that drives us how much grid forming BESS should be sized to achieve that Q by V or P by theta response. Now, in the previous slide, I said that this particular grid forming BESS is providing SCR of 1.9. I should be more exact. What I'm really trying to say is that it is providing short-term active and short-term reactive power response within that transient to subtransient time scale, so that the grid looks like, so that it is behaving as if the grid strength in the dynamic sense is 1.9. So instead of calling it SCR contribution, because it's not really providing 1.9 per unit of short circuit currents, it is providing the short-term dynamic grid support. Maybe we can call this dynamic SCR or DSCR. Now, once you have sized the grid forming BESS using this approach, we can you can always use models like on the right side, where we have used models of the IBR and the BESS to find out if it is accurate or not. So, but without models also, we can do this based on understanding the deficit between the demand for grid strength, available grid strength, using simple metrics that we all understand, SCR, and then translating that deficit to a watt per volt and watt per theta response. So with that, I think that is the end of our presentation. So thank you for your attention and look forward to questions. Julia, back to you.
Right. Thanks so much, Nilesh and Shahil, for an interesting presentation and sharing the results. There are a lot of questions. We'll go through some, and then I'll ask you to answer the rest of them offline. What was the actual sampling rate resolution for measurement device, and which voltage level were measured? That's Nilesh, to you, I guess.
Yeah, so it was through the PMU was a 50 hertz samples we received. We also requested Elspec data, so that help us to even extract 50 hertz samples, or even higher hertz or lower time resolution samples to understand this this phenomena.
Good. The next one is the oscillation amplitude was small. How was the problem first identified? Do you have tools which look at small amplitude oscillations in voltage in real time?
So at the time when we identified this oscillation for the first time, we were investigating in this incident, a line trip incident that happened in that part of the network. And to investigate that incident, we looked through the 50 hertz PMU data in that part of the network, and that's how we came across this these oscillations. Sorry, what was the second part, Julia? This question.
It asks if you have tools in real time that monitor for oscillations.
So since then we have requested NSPs to install a lot more PMUs in that part of the network. So now we are getting that PMU stream into our system, and we have a automated script which detects this oscillation, and if it lasts for more than certain amount of time and the magnitude is higher than a threshold we provide into the tool, it sends us a notification. So there is a auto trigger identification put in place as we speak now.
And since maybe Nilesh, since you mentioned the magnitude, there is another question that's slightly lower in priority, but I'll ask, given the relatively small magnitude voltage oscillations, how important will this phenomena be to overall control of IBR systems?
It's a very good question. I think we are looking at that how high could be a problem or how low could not be a problem. So right now there is a work in progress to identify this the magnitude of oscillation above which we should be really worried about it. So drawing a line between between a nuisance to the grid to the system security issue. So that's still a work in progress. But any oscillation on the grid is not really a nice thing to see. If there are, if it creates a resonance, any kind of resonance, which is hard to see during real-time response, that's not really good for the system, overall power system, and could lead to a damage to the equipment. So in terms of magnitude, what should be the threshold above which system operator should be worried about, that is still work in progress.
That's good. When you said, Nilesh, the one to you as well, when you said that DC link control strategy was improved, can you expand on what was actually improved? Was it the tuning, the gains on DC link controller or MPPT?
Yeah, so this was done by OEM, and there are some proprietary information which sits with OEM. Coming from the system operator perspective, what we want to know is whether the solution works or not. So unfortunately, wouldn't be able to provide a lot more detail about than what I mentioned. It's more of improving the DC link control of the plant.
Next question, kind of related. Why make use of HVDC controllers to dampen oscillations that are seemingly caused by inverter controls at solar site? Why not change IBR controls on solar site?
Well, it is possible to look at other options in place, like using the other devices to damp this oscillation. That's also option on the table, but I think the interest at the time was to find the cause of it, and then if we can work with the cause of those oscillation, and then try and reduce from the source, that's much more beneficial rather than trying to work with another IBR, and then that can provide a positive damping to this oscillation. So at the time, looked at the source of the oscillation and work with generators and OEM to fix those issues.
I think I'll skip the next one. The next over is, did the oscillations die on their own, or and if yes, how long did they last?
So they were disappearing by its own when they were present in the grid. So there was one slide where I showed that gradual increase and then gradual decrease of the oscillation. So they were disappearing by itself.
Next one is, I'll ask it, but I think you talked about that already. Wouldn't the change in irradiance impact the real and reactive power output of the IBRs?
It would definitely impact the response or the real and reactive power output of the plant. But the reference of the power from the PPC was still a constant. They try and probably generate more than they could through the irradiance. So that could be probably cause of this source of oscillation. But yes, the irradiance change would definitely change the active and reactive power output.
The next question is kind of similar, so I'll skip that one. If PMUs were sampled at 30 samples per second, which I think is set 50, right? How can 18 hertz and higher be detected in real time?
That's a very good question. I mean, normally it's a 1/3 is a Nyquist criteria, right? So 50 hertz sample would probably give 1/3 of 50 hertz with a great confidence. But when you look at the sample, you could potentially see very, very close to 17 hertz. You can still see it. So 50 hertz sample per cycle doesn't mean that you wouldn't be able to get the 17 hertz oscillation. And some of the figures which I show where the data coming out from 50 hertz resolution, so 20 millisecond resolution. So it should be able to pick up 17 hertz to a certain extent. We also looked at the LSPEC data, which is very high resolution, did the FFT on that, and then we could easily see 17 hertz through that as well. So there is a bit of a hint that there is an option to look at 17 hertz through 50 samples per cycle.
Kind of able to confirm that from that. Did you analyze the effect of basewater and rearing large synchronous turbine generators? I guess that's a local question.
That's correct. So that's those two plants are far away from waste Mori areas.
So no effect. There's a question, how was the EMT modeling achieved? So I guess like if you want to expand on that a little bit.
Yeah, so we through this generator connection process, we receive EMT model for the site. They are normally vendor specific and site specific or vendor site specific model. We integrate those model and make a wider area model which has plants, SVCs, HVDC, and the lines. And we use those model to understand this kind of phenomena. So not sure what's the exact question of it, but we do have a kind of a luxury of using a site-specific model, at least in AEMO.
Maybe I'll add to that. Like you were, I think in slides you showed that you were able to replicate the oscillations in the models. Have you found anything kind of interesting regarding those models? Were those like completely accurate? Were there anything unexpected that you found while doing that exercise?
Nothing I could think of at this stage we could find unexpected. At least it helped us to replicate the incident, and it also provides the confidence in the model. So if we this was example where there was a real-time incident which we could replicate through the modeling. But even in a modeling analysis, if you see something, then you could give a faith or at least have a confidence that okay, this could be a real thing.
Yeah, and just a point to add, basically, the EMT models also give you can show you the oscillations that you have not observed in the field. For example, if there are certain modes which have sufficiently high damping in the current grid conditions, so that's why they have not manifested as oscillations in the field. So we did see some modes with positive damping, but they are something that we haven't seen it in the field measurements.
Yeah, and there was a related question down the line there about could you have anticipated this oscillations events? Like if you have this accurate models, could you have anticipated those through planning studies somehow?
I think what Shahil is mentioning is probably correct, that with this model we could have get a more understanding of it. This was more of a like what we saw on the field and try and replicate it. But using this model, at least in the planning time frame or operations planning time frame, we could easily pick up things that might affect the system. So if there are some outages happening in that part of the network or any other part of the network, if you got the models, then you can run through the simulation. And if you see some kind of control interaction, that help us to put mitigation measures while during those outage conditions. So definitely helps to in the planning time frame.
Thank you. Shahil, next one is for you. Impedance scans only cover small signal stability. How do you make sure stable operation under low SCR condition is achieved with large disturbance?
So I think many of the times when we do the LVRT test, when the vendor does LVRT tests, they are usually they pass through those tests, and the grid strength is not really a huge factor in determining the ride-through behavior of IBRs, because your voltage is already dropped to zero. Now, if they are able to ride through zero voltage, like zero voltage events for a few hundred milliseconds, it doesn't really matter whether the grid is weak or strong. What happens is that when the IBR comes out of that event, then the grid strength becomes important, because now you have gone through a big, large event. And if the grid is weak and the stability margins are low, then that might result in tripping or oscillations. Sometimes you see those oscillations when the IBR is coming out of the event. Sometimes you don't. It just goes into tripping. But many times the small signal stability is the key factor that differentiates between IBR not riding in the field, riding through the events in the field, but right through all the LVRT requirements. So small signal stability is still kind of sometimes can be a core factor in transient events or transient stability.
Thank you. So we're about at the top of the hour, and I'm going to wrap this up. I would like to thank Nilesh and Shahil once again for their presentation today. As I mentioned earlier, an email will go out once the video file has been posted, and we will get answers to all the questions that we didn't get to during the webinar. We'll post those as well as quickly as possible. We appreciate your engagement and look forward to seeing you again soon, perhaps at the February 26th webinar, which is the next GPST ESIC webinar on reliable energy forecasting for power system operations, which will be done by researchers from Imperial College London. Further information on all our webinars and meetings can be found on our website at www.esic.energy under events and our newsletters and informational emails, and you are all invited to attend. Nilesh, Shahil, thanks once again for this very timely and informative webinar. And thank you all for your interest and for your questions. We look forward to seeing you again in the future. Thanks so much. Bye.
Thanks, everyone.